The thing we're going to talk about today is gravity, okay? Now, gravity has been a really big point of contention for a lot of people, especially in the flat earth community. A lot of people say, well, gravity doesn't necessarily exist. It doesn't have to exist. Everything can be handled simply by density and buoyancy, okay? Well, that may be true, and it probably is true to a large degree, but it's always been my contention, essentially, that there is something that is determining up from down, okay? Once you determine what that up from down actually is, then it makes it a whole lot easier to actually define, what gravity is, or buoyancy and density, excuse me. So what we're going to talk about today is a couple of things. First of all, why the mainstream model of gravity is such utter nonsense. And I'm also going to propose another model today that is not my own model. This is another model. There are actually several other models of gravity that have been proposed by lots of other physicists, much of them that were a lot smarter than Einstein, and Newton for that matter. And it's more of a 20th, 21st century type of model of gravity, okay? So basically, we have the mainstream has two different kinds of gravity. There is the Einsteinian model, and the Einsteinian model is the type of gravity where space and time actually bend, okay? They actually distort. Many of you may have seen the demonstration by the physicist teaching his college class. He had a big circle and a big cloth of like lycra stretched out over it, and he rolls the balls around, and basically they kind of roll around until they hit the center. Well, what he's trying to illustrate there is a actual distortion in space, okay? So, but the bad part about that, of course, is he's using gravity to demonstrate gravity, or gravity to define gravity, which really doesn't work too well. So that's one idea, and of course that type of gravity comes out of Einstein's relativity model, which many people disagree with, especially Nikola Tesla. He had absolutely no use for it whatsoever, and it really doesn't fly, especially when you consider all the imaginary factors you have to take into consideration with it. And we'll kind of touch on those just a little bit. So the other model of gravity is the Newtonian model. And of course, we've all heard about this. This is where anything that has any mass whatsoever will tend to have an attraction to anything else with a mass. Okay? Masses attract mass. Great. The universities will try and demonstrate this with what's called the Cavendish experiment. Of course, many of them are very unsuccessful. Many of them are actually dealing with another force that they're not necessarily explaining to the students because it simply is not taught in the mainstream paradigm. So we have those two basic models of gravity, and at least I will say this about Newton's model of gravity, even though I don't believe for one second that masses attract other masses, and really that's a very, very difficult thing to prove, and in most cases it's fairly easy to disprove. But at least Newton's model of gravity gives us something that we can work with, that we can do basic physics here on Earth to predict the behavior of gravity and mass and inertia, okay? So that kind of works, and the math that's built around that actually works. So, most people actually use that. Now, when you get into Einstein's model of gravity, that gets really, really abstract. It gets into, dealing with, well, just like Newton's, it gets into dealing with different types of masses. And, of course, mass is one thing that, if any of you are followers of Globebusters, we just did a show on that about a little over a week ago, called Flat Earth Sunday Mass, and it was all about the huge anomalies with what mass actually is. Some physicists will say, well, in the simplest form of mass, it can essentially be equated with weight. And in fact, the SI unit for mass is the kilogram, which of course is also a unit of weight. After that, it gets a little bit weird because then they start getting into charge potential, and whether or not mass running at a velocity actually increases in mass like Einstein predicted or not, and there's a huge disagreement on that. But Einstein made the prediction that once mass starts moving and accelerating and it approaches the speed of light, because of the kinetic energy that's actually in motion there, the mass starts to become larger and larger and larger, and as you get towards the speed of light, it actually starts to become to a point where it's infinite, right? Well, an infinite mass is kind of ridiculous because really we know that there isn't anything that's infinite at all in this universe, except maybe the universe itself, but we don't know that. So you really start dealing with a lot of abstracts when you get into mass and also energy. One thing that is not very well understood is that energy is not very well defined either. And there are several schools of thought on it, and it has ultimately led us into what they're trying to detect, these subatomic particles, quarks and gluons and things like that. And the mass of the mass is mostly taken up by the protons in an atom in the nucleus. And it gets very, very, very confusing. And really, nobody has any idea what mass really is. It's almost an impossible thing to define. So that's one of the big problems with gravity. So one of the things, there's actually two different kinds of gravity. One is called big G, okay? And big G is what's called the universal gravitational constant. And that is like what Newton said, that's attractions of objects with mass to one another, okay? And it's actually measured in newtons, okay? Newton is the psi unit of force. It is equal to the force that would give a mass of 1 kilogram and acceleration of 1 meter per second, so 1 meter per second squared, essentially. Okay, so, as I addressed earlier, mass, what does that have to do with gravity? Well, apparently, again, that's a school of thought that is not very well known, especially since they really don't know how to define mass properly. But they do have a formula for it. And the formula is expressed in the force of attraction between two bodies. And the formula is F equals G times m sub 1 times m sub 2 over r squared. And what that essentially means is F is the force of attraction between two bodies, G is the universal gravitational constant, m sub 1 is the mass of the first object, m sub 2 is the mass of the second object, and r is the distance between the centers of each object. Great, okay, I'm sure that went right over most people's heads. So we also have little g, okay? And little g is essentially defined as the acceleration of objects towards the Earth, like when they're in free fall. And most people know that. It's defined as 9.8 meters per second squared, or 9.8 meters per second, okay? So now that I have kind of given you the specifics of what's going on with gravity in the Einsteinian and Newtonian models, we have a couple of questions that we need to ask about it. First of all, can we detect gravity? Or can we simply observe its effects? Like Neil deGrasse Tyson comes out and holds his microphone, drops it on the ground, said, that's gravity, right? That, I suppose you could say, is him demonstrating it, that observing its effects. But detecting gravity is an entirely different story. So science basically has been unable to reconcile the celestial motions, okay, using the gravitational model that Newton came up with, and of course this is part of the reason that Einstein came out with his model in his special theory of relativity and extensions of that work. So that they could essentially go out and invent all kinds of more imaginary things and things that are unprovable, things that are unobservable. It's just a very, very difficult thing for people to actually comprehend, because even the physicists themselves, as I demonstrated on Globebusters a few weeks ago, cannot agree at all what mass is or what gravity is. So they have come into, this model that's essentially fantasy land. Okay. So, no pun intended. Yeah, no pun intended. So, they have spent billions and billions of dollars on facilities like CERN, looking for the Higgs boson particle. And of course, this magical Higgs boson particle is the thing that supposedly gives matter its mass. Well, they really haven't detected that. They claim to have some inklings of it, but there's nothing concrete of it at all. And of course, the idea that they would be able to do that really is kind of ridiculous, because they operate on the premise that there are massless particles. Now, that is kind of an oxymoron for most people. How can you have a particle that doesn't have mass, right? That actually makes no sense, and a lot of people, a lot of physicists, not just myself, disagree with this particular concept. So what they have done is they have created these facilities, CERN, to detect that, and they've also created LIGO. And LIGO is, a multi-billion-dollar operation, and they actually have several facilities around the world, but there are 2 in the United States, to be able to detect gravity. Okay, so go ahead and bring my screen up real quick, because I'm going to do some screen shares. Okay, so a long time ago, in a galaxy far, far away, there allegedly were 2 black holes that came together and collided. And theoretically, when that collision actually occurred, there was supposedly a great ripple in space-time, because again, we're operating from the assumption of Einstein's model of gravity, where space and time are actually curved, and they're also linked together at the hip. Okay, so about I think it was 1.4 billion years ago. Yeah, that's right. Let me make sure I got this right here. 1.4 billion light years away, this actually happened. And of course, the reason I say a long time ago in a galaxy far, far away is, 1.4 billion light years is a long, long ways away. And it took 1.4 billion years to actually get here. And when that happened, it sent out a great distortion in space-time. All right? So this distortion in space-time is so severe that it just travels and travels and travels through space-time at the speed of light, until it finally arrives at Earth and is detected by the LIGO detectors precisely 100 years after Einstein makes his prediction of gravity waves and how they could potentially be detected. But even Einstein himself said that it was highly unlikely that gravitational waves would ever be detected. And really, I hold that that is still true to this day. So what I'm going to do is I'm going to show you a couple things here. And what we have here is we have an article by space.com. And like I said, it was about 4 or 5 years ago. They actually found these gravitational waves, so they say. But there has been a huge backlash from a lot of physicists saying, no, you didn't. This was a complete false signal. This is not what's going on at all. And of course, they go on to explain how they found it. They talk about these 2 black holes here that are colliding together, okay, and then sending out that wave through space-time. So we have 2 LIGO sites, one in Hanford, Washington, and the other one in Livingston, Louisiana, okay? And the way that these things work is kind of interesting. And they work on something that has never been proven or never been demonstrated in any way, shape, or form, that gravity waves actually distort physical space and time. That has never been proven. It is just a mathematical assumption. And it's something that they're operating, and they've spent billions of dollars on to try and prove this. So here's what they say about how these things work, okay? So a laser beam is split down 2.5 mile or 4 kilometer arms containing mirrors. The laser beams reflect off the mirrors to converge at the crux of the arms, canceling each other out. The passage of a gravitational wave alters the length of the arms. Okay, again, so they're saying when this gravitational wave comes in, it cuts across those arms and it physically changes the length of them, which, of course, has never been demonstrated and is utter nonsense, okay? Canceling each other out. Okay, the passage, okay, oops, I'm sorry. The mismatch is measurable with a light detector, okay? And this is this laser interferometer, and I'll kind of explain that in just a second. LIGO facilities in Louisiana and Washington State operate simultaneously. The two data points allow a triangulation of a wave source in the sky. Okay, and down here they have this little footnote that says, using laser beam, scientists could detect the physical distortion caused by the passing of gravitational waves. All right, so what's happening? So let's look at this little diagram here. So what they're saying is happening is they've got the laser that's firing off, and it's going into this beam splitter, okay? And one part of the beam goes off in one direction, and the other part of the beam continues straight through, okay? And what's happening is they're bouncing back, and then they are recombined, and then they go to the light detector. And what that light detector is doing, essentially, is looking for a little bit of phase differential between those two light waves, okay? So if you have light waves and you have things both in sine waves, right? When it leaves, they're perfectly in sync, like this. And when it comes back, if there's a distortion, if there's a detection, one of those will be slightly out of sync with the other, all right? So that's essentially how they're doing this. But the crazy thing about this is they say that over 4 kilometers, that when this wave passes through, it causes a distortion of about 1/1000th the width of a proton. Now, think about that. 1/1000th of the width of a proton over 4 kilometers. First of all, I would suggest that that is not even possible to detect something like that. The premise is absolutely ludicrous, and it, again, like I said, has never been actually demonstrated that any of these space-time distortions have ever actually happened. So, LIGO is basically a bunch of nonsense. So let me get on to my next thing here. And now they also have several other facilities. They have the 2 LIGO facilities in Hanford and in Louisiana and in Washington, excuse me. But they also have other laser interferometer detectors that are around the world. They have the Virgo detector, which is in, I believe, Europe somewhere. I'm not sure where it is here. European Gravitational Observatory. They have the GEO 600 in Germany, and they have CAGRA, which is in Japan. And it's very interesting that since LIGO has detected its gravitational waves twice, the other facilities had not detected gravitational waves, but now all of a sudden they are detecting in the 3rd and 4th instance. But they've gone, all these years that they're, since they were first set up without ever detecting so much as a peep, all right? So it's obviously not a very reliable model to be able to predict anything. And not only that, I would add that, don't you think that it's a little strange that they're talking about gravitational distortions that are coming from a source 1.4 billion light years away, and yet here we are, swimming in a gravitational field that is supposedly caused by our own sun, our own moon, our solar system, the planets going back and forth. Full moons affect people profoundly. Full moons supposedly, and the moon supposedly has a very profound effect on tides, right? Well, so if you think about that, you have to ask yourself, why is it then, if these LIGO detectors are so sensitive as to detect any type of space-time distortion or any type of gravitational field, especially a strong gravitational field, one would think, right, that the moon, when it passes over and it's going over the oceans and it's lifting up thousands and trillions of tons of water, right, causing the tides, that you would think would be an extremely strong gravitational field. But lo and behold, it has no detection whatsoever. And not just the moon, but any planets going around. But, I cite the moon because that would be one of the largest gravitational distortions ever. And they tell us, like I said, mainstream tells us that this gravitational pull of the moon lifts up, all this ocean water. And yet, when the moon passes over the LIGO facilities, not a peep. Can't detect it. So that doesn't make any sense to me at all, and I'm sure it doesn't to you either. Why is it they can detect something that's 1.4 billion light years away, and they can't detect something that's allegedly 239,000 miles away that is so profoundly affecting our oceans? All right. Well, that's obviously a huge enigma, another one of those big anomalies that you have to kind of go, that doesn't make a lot of sense. So basically what we're going to talk about now, you can tell really that they don't really have any clue what gravity is. They're searching in the dark. They are operating on a ton of assumptions that none of them make any sense whatsoever, have never been proven, have never been demonstrated. When you get out into the solar system and the cosmos, suddenly the gravitational model that applies on Earth no longer applies to the planets or the stars or the galaxies. And this is where they have to start inventing things like black holes, which have never been seen, inventing all these celestial events, which again have never been seen. So, they've literally gone off the deep end, in mathematical equations, and they have nothing that is observable and nothing that is truly measurable. It is all based on absolute hypothesis. Okay? So a lot of people realize this, and they realize the nonsense of it, and so they have come up with a different model of gravity, and that is the electrostatic dipole alignment model of gravity. And like I said, this is not my model of gravity, but I do support it because I think it makes a whole lot more sense, and we're going to give you some practical demonstrations of it. But the first thing I need to do is kind of get you in tune with what that actually means. And what most people don't know is that the Earth itself generates a huge electrostatic field, okay? Most of us can see it in lightning and, during thunderstorms or sprites and elves where we see discharges going up, and seemingly plateauing out. And my contention of that is, I believe that there is a firmament up there. I believe there's something up there that they are calling a firmament. I'm not a religious person, but I do follow the facts, and all indications are that there is something up there, and I have lots of other reasons for thinking that. But we do know for a fact that the Earth generates a huge electrostatic field, and it is always, always there. So I'm going to play this video really quick and just kind of give you a little primer on what mainstream science says about this electrostatic field. So I'm going to go ahead and play this, and here we go. Oopsie. We are not getting any sound. Oh, sorry, my bad. Let's try that again.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures. To take advantage of this...
Okay, all right, so even the mainstream model, mainstream science acknowledges that this field actually exists. We've all played with static electricity. Everybody's taken a balloon and rubbed it against their hair and maybe drawn it towards water, and it draws the water towards it, or anything. You can literally affect anything with electrostatic energy. It doesn't matter what it's made out of. It doesn't matter if it's glass. It doesn't matter if it's rubber. It doesn't matter if it's wood, metal, anything like that. Electrostatic energy, electrostatic force, actually has an effect on all of it, and this is easily demonstrable in science. There really is no material that is immune to electrostatic force. And really the reason for that is because all particles are made up of atoms, and atoms are made up of charged particles, okay? So charged particles, again, is a charge just like the charge in the atmosphere. Everything has a charge to it, okay? So we're going to move on a little bit further, and this next guy, I cite an awful lot on Globebusters, and his name is Ken Wheeler. His channel is called The Theory Apophysis. And he's going to really, really ultra simplify something that really hit home for me and made me start researching this a lot. And what he's going to talk about, again, is a very simple analogy and what actually he believes gravity is. Now, Ken, this guy is an absolute genius. He's kind of a weird guy, but he is absolutely brilliant. He is respected the world around. He's probably the world's foremost authority on magnetism. And he's an amazing guy. So let's hear what Ken Wheeler has to say about what gravity actually is. Here we go.
Okay? Gravity is nothing other than dielectricity. Gravity is no different than turning on your TV set and actually shining a light off from the side and seeing the little dust particles actually head to the TV set and stick to the TV set. That's why your front of your TV set, especially the little CRT tubes, got so dusty. The dust in the air would go gravitate to the front of the... That is the exact same thing as gravity. People think that is an electrostatic charge, or like you charge a balloon up and you pull someone's hair to it. That same acceleration, not force, that same acceleration is what we ignorantly call gravity. Gravity itself is an autonomous acceleration, of which a lot of people call it incorrectly a force, does not exist. It's like, what do you mean gravity doesn't exist? Obviously I can drop this and there's gravity. What I mean specifically is that gravity does not exist. It is not an autonomous force. It's definitely not a force, which of course even the idiots of general relativity and quantum mechanics will admit to. They call it an acceleration. But an acceleration of what? By what? We need explanations, not descriptions. And all that general relativity and quantum mechanics provides are descriptions, not explanations. It is a dielectric acceleration. It's dielectric avoidance. Okay? It is the loss of force in motion, because there are no straight lines in the universe. What we think are straight lines in the universe are infinitely slightly curved. There's not a single straight line anywhere in the universe. None, nowhere, ever, never. It doesn't exist. So, hope I made that very simple. We have one field. We have the loss of that field expressed as force in motion, and we have two field modalities. One expressed as a dielectric condensate, which we call matter, mass, okay? And the other one, which is expressed by longitudinal transverse force and motion, transverse electromagnetism expressed in frequency and amplitude, what we call electricity. So dielectricity, electrostatics, electricity, magnetism, and quote-unquote gravity are one thing only. It's our only pathetic human understanding of the nature of the universe that we think these are four separate things. Really, they're just one thing. They're a hydra, a single beast with four heads, if you want to talk about it that way. Thanks for watching.
Okay. So what Ken is saying there, the most important things that he's saying, first of all, is that he talks about dielectricity. Now, dielectricity can be analogous to what we've all heard about the ether. Okay? Now, the ether was dismissed by Albert Einstein, and this was the result of several experiments that were done over 100 years ago, Michelson, Morley, Sagnac, Airy's failure, etc. And the mainstream world simply couldn't handle it, so they, had Einstein come in with his theory of relativity. The other thing that Ken said is that all these forces that we're separating into four different things, the gravity, electrostatic force, electromagnetic force, dielectric energy, are all the very same thing. They are all byproducts of each other. Most people understand that when you have a current flow or an electricity flow, it generates a magnetic field. You can also generate a magnetic field, cut it across a conductor, and it will generate a current flow. Okay? So these are all very, very much tied together. Okay? So that's what we're going to take away from Ken Wheeler in that. So next up, we're going to go to a guy, and this guy is a physicist from Australia. His name is Wal Thornhill, and Wal works on a project called the Thunderbolts Project, okay? And this is the electric universe model. And this model is up and coming very rapidly, and it is disproving mainstream cosmology left and right, and replacing it with a model of an electric universe, saying that everything is in fact based off of electricity. And the evidence that they have for this is absolutely overwhelming. Mainstream people do not like it because it completely destroys their cosmology. It makes astrophysicists and astronomers and all this stuff have to completely rethink their model, redefine it from the get-go. And most importantly, it proves Einstein dead wrong on every single account. Okay? So we're going to listen to Wal, and the first thing he's going to talk about is the scale of an atom and how actually small it is. So I'm going to play just a few minutes of this, and he's going to talk about this, and he's going to talk about a guy named Fritz London, who invented the London force, or discovered the London force. It was named after him, and it's basically what happens when a gas condenses into particles. Okay, so let's listen to Wal here for just a minute.
Now, if we're going to talk about particles and matter, we have to look at the scale of the atom to give you some idea of what we're talking about. The first step, then, is to give some idea of scale. As I said before, modern particle theory is no help because specialists were still arguing over what is really real in nature last month. This picture gives an idea that the classical atom is mostly empty space, with the charged particles invisible on this scale. It is easy to see how an electron orbiting the nucleus can only shield the nuclear charge from a nearby atom for a fraction of the time it takes in its orbit. Because at some points, or most of the points in the orbit, the proton, for instance, the charge on the proton is visible to a nearby atom. And the same thing for the other atom. So it gives you the idea that if those two atoms can synchronize their orbits, they can then come together and form a molecule. So, as it says there, if the nucleus was the size of a ping pong ball, the electrons would be the size of a flea orbiting outside this stadium, which is in Melbourne Cricket Ground in Australia, at one of our, which causes gas molecules to condense.
Oops,
1930, Fritz London explained the weak attractive dipole electric bonding force between atoms, known as the van der Waals dispersion force, or is named after him also as the London force, which causes gas molecules to condense and form liquids and solids. In other words, planets and you and I and everything in the visible universe. The London force originates in oscillating electric dipoles caused by slight distortion of otherwise electrically neutral atoms. So here we're talking about the kind of stuff that the Earth and the planets and the Sun that are made up of. The tiny electric dipoles arise because the charges within the atom are separated, as shown in the last slide, by effectively a huge distance. The electric dipoles resonate, as I said, they sort of tune into each other and orbit in such a way that they combine. It's always attractive, just like gravity. So there's a clue. So, in fact...
Okay. So, basically, he's talking about another force that Fritz London discovered, the London force, and how what's actually happening is dipoles are actually lining up with each other, just like a string of magnets, okay? If you have a magnet, you have a north pole and a south pole, and you place a magnet on a table, it goes north, south, north, south, north, south, they'll all stick together. That is because they are actually aligning their poles, okay? The same thing happens, essentially, with atoms and atomic structure. So the crux of this theory essentially is that you have these electrostatic dipoles, and they are formed inside of atoms, and what's happening is you have the Earth down here at the very bottom, okay? And the Earth would be negatively charged. And in the electric universe model, they have a little bit different take on what the positive side of this circuit actually is, and that's through dielectrics of the atmosphere itself. But in the flat Earth model, I would suggest that we need to make a slight modification to this and say that the positive side of this is actually the firmament, okay? Everything makes a lot more sense when you have a complete circuit with the Earth as the ground and a firmament up above that is positively charged. Okay, so what's happening then is since we are all made up of atomic particles, all the molecules in our body, all the molecules in everything are made up of atomic particles, and they are charged. You have the electron being negatively charged, you have the nucleus being the neutral charge, and of course the proton or positron is the positive charge of this atomic structure, okay? So again, just think of it in terms of a magnet, okay? These little atoms are lining up just like a magnet does, north-south, 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 north-south. And what he's showing here is that the nucleus, which is about 1,800 times larger than the electrons that are orbiting it, is being pulled down by the negative electric charge of the Earth itself. Okay, and as it does that, it actually causes the electron to become slightly more positive. So there's just a very, very slight distortion in the atomic structure. And it's a very, very weak structure. However, when you sum all of the aligned subatomic particles, you essentially get this profoundly weak force of gravity. So again, what we're saying here is the electrostatic force is all around us. We're swimming in it. It's a field all around us. And that everything that is within it is subject to this dipole alignment effect. It's a very, very simple model. That's really all there is to it. So how do we prove stuff like that? Well, there's a couple things that are really interesting. And Rick, we may run a couple minutes over anyway. But I'm going to play a clip here. Maybe I should just go to this one. I'm going to play a clip here that talks about some creatures in nature that actually take advantage of this. One of the creatures that they have found has very strange anti-gravitic type effects are bumblebees. Physicists have told us many times that, when you do all the math and look at a bumblebee, they theoretically should not be able to fly. Well, now they found that in the structure of the wings, they've got these hexagonal structures that literally the bee is able to mediate the charge on them. Okay, so what's happening is the bee is able to change the charge potentials of these little hexagonal things in its wings. The same thing happens with a creature called a scarab beetle, okay? And the scarab beetle, there was a gentleman that actually designed a craft that he was able to actually fly around out of scarab beetle wings, okay? Crazy stuff. But all this stuff is very, very real. But one of the most interesting things was just brought out by the University of Bristol, and this is a very, very recent, this was just last month that this came out. And you've all kind of seen spiders fly around and float, and in fact spiders get on ships. You have to wonder how they get there. It has been the mainstream theory up until now that what's going on with these spiders is they are shooting out basically a little bit of silk thread, and the wind is catching it, and they're kind of floating around on it. Well, the University of Bristol just discovered something quite different and quite astounding about that, and we're going to go ahead and play this video so you can check this out. This is amazing.
Of all the great flyers the world has ever known, it may come as a surprise that one of the best aviators in the animal kingdom doesn't even possess wings. Spiders, instead, use long fans of silk to carry them through the air, often for many hundreds of miles, in a process known as ballooning. They have long been known to have flown the nest in such a way. Charles Darwin himself marvelled at hundreds of tiny spiders landing on the Beagle while out at sea, and later recorded how they took off from the ship with great speeds even on a calm, windless day. During this time, there were two theories for how ballooning worked. The first theory, and the most obvious explanation, was that long strands of silk emitted by the spider catch the wind and the associated drag forces pull the spider aloft. But spiders will only balloon on days where the wind is a gentle breeze, which raises the questions of how there'd be enough force to pull the silk from the spider's spinnerets, and how could heavier spiders even become airborne at all. The second theory was that atmospheric electricity could also provide the force needed to get the spider aloft. Similar to how your hair lifts to stand on end when you rub a balloon on your jumper, spider silk could be lifted into the air by natural electrostatic forces in the atmosphere. These electric fields are present at all times all around the world, but are most noticeable during thunderstorms when they are at their strongest. Surprisingly, until now, the electrostatic theory of spider ballooning had never been tested. In our lab at the University of Bristol, we isolated spiders from any airflow or atmospheric electricity and generated our own controlled electric field at levels found in nature. In response, the spiders began to change their behaviour to perform tiptoeing, where they straighten their legs, raise their abdomen and release silk. This behaviour is only ever seen when a spider wants to balloon. Furthermore, once the spider was aloft, its altitude could be controlled by turning the electric field on and off. This demonstrates that spiders can balloon using electrostatic forces alone, but in all likelihood they would use a combination of both wind and electricity to balloon in their natural environments. So how do the spiders detect these electric fields? In this experiment, it was also observed that the minute sensory hairs on the spider's exoskeleton were similarly moved by the electric field. We can then infer that spiders can feel the charge in the air using the same sensory hairs they would use to detect a breeze. The results of this study show us that electrostatic forces could be an integral part of spider ballooning. And by fully understanding the mechanisms behind it, we can better describe population dynamics, dispersal, and ecological resilience, all of which are important for global ecology.
All right, so there we have it. Nature performing its miracles. And I actually have another clip here of a gentleman that is a Lockheed engineer that is talking about how all you really have to do is understand what's going on in nature, and we can replicate these anti-gravitic forces. And he talks about them being directly related to magnetism. And of course, as Ken Wheeler said, magnetism, electrostatic energy, gravity, dielectric energy are all one and the very same thing. So that's pretty much that. Now, one other thing I did want to say is just going back really quickly here to LIGO. And I don't have a lot of time to elaborate on this, but what I do want to say is when you look at the way this works, when I first saw this, I thought, wow, that's really amazing. Where have I seen that before? And then it occurred to me that this is where I had seen this before, and many of you may possibly heard about the Michelson-Morley experiment. And the object of the Michelson-Morley experiment was to detect Earth's 67,000 mile per hour motion around the sun. Of course, it came back with a null result. And the reason for that, they said that was something that was called a Lorentz contraction that caused the arm that was moving in the direction of the alleged Earth's rotation to shorten, okay? So that was their excuse for it. But now here we have today the very same thing in LIGO. We've got, here's the Michelson-Morley, you've got the light source, which is being split, going to two mirrors and then coming back to an eyepiece, which is generating an interference pattern. In principle, it is absolutely identical to what we see going on here with LIGO. And isn't it interesting that LIGO, for whatever reason, is not having this compression problem like they claimed was the problem with the Michelson-Morley experiment. Anyway, that's all the time I have, guys, but thank you so much. And if you want to hear any more elaboration on this, I am the host of the Globebuster Show. We are on every Sunday at 12 noon Pacific time, and we will certainly be elaborating on this more for all of you. Thank you.
Thanks so much for watching. I hope you enjoyed this video presentation. If you did, please subscribe to my YouTube channel, like the video, and share it on your favorite social media sites. There's a lot more to come, so stay tuned and we'll see you back next time.